much of the brain is removed. Michael Talbot wrote, "Even after removing as much as 90% of a rat's visual cortex, the part of the brain that receives and interprets what the eye sees, he found it could still perform tasks requiring complex visual skills. Similarly, research conducted by Pribram revealed that as much as 98% of a cat's optic nerves can be severed without seriously impairing its ability to perform complex visual tasks. Such a situation was tantamount to believing that a movie audience could still enjoy a motion picture after 90% of the movie screen was missing, and his experiments presented once again a serious challenge to the standard understanding of how vision works. The orthodox explanation of vision is that the eye sees by taking a photographic image and reproducing it onto the cortical surface of the brain, where we interpret it like an internal movie screen. Dr. Lashley's experiment showed, however, that even when 90 to 98% of that internal projector screen is missing, the brain still receives and registers the whole movie." Greg Braden wrote, "Experiments demonstrated that animals retained memories and continued their lives even though the parts of their brains that were believed to hold these functions were removed. In other words, it appeared that there wasn't a direct correspondence between the memories and a physical place in the brain. It was obvious that the mechanical view of brains and memory wasn't the answer. Something else strange and wonderful must be happening." These and other experiments have shown that Dr. Lashley's engram theory of individual memories existing in certain areas of the brain is provably incorrect. Memories and images are distributed all throughout the brain, just like a picture is stored all throughout a piece of holographic film. Michael Talbot wrote, "Paul Pietsch began as an ardent disbeliever in Pribram's theory. He was especially skeptical of Pribram's claim that memories do not possess any specific location in the brain. To prove Pribram wrong, Pietsch devised a series of experiments. Pietsch reasoned that if a salamander's feeding behavior is not confined to any specific location in the brain, then it should not matter how its brain is positioned in its head. If it did matter, Pribram's theory would be disproven. He then flip-flopped the left and right hemispheres of a salamander's brain, but to his dismay, as soon as it recovered, the salamander quickly resumed normal feeding. He took another salamander and turned its brain upside down. When it recovered, it too fed normally. Growing increasingly frustrated, he decided to resort to more drastic measures. In a series of over 700 operations, he sliced, flipped, shuffled, subtracted, and even minced the brains of his hapless subjects, but always when he replaced what was left of their brains, their behavior returned to normal. These findings and others turned Pietsch into a believer. Salamanders were good subjects for this experiment because they simply go comatose when their brains are removed, and then quickly regain normal functioning once it's replaced. In Dr. Pietsch's 700 trials, he subtracted sliced, diced, mashed, and even sausage-ground salamander brains, but no matter what, after putting back whatever was left of their brains, they always regained normal functioning. David Icke wrote, "Mainstream science has been unable to locate the area of the brain that contains all the memory, because what we call memory exists throughout the brain and body. This must be the case, because it's a hologram. People with tumors, who have large parts of their brains removed, do not lose specific memories. They might not remember, in general, quite as well, because they have moved to a smaller level of the holographic memory where there is less clarity than in the whole. But they don't lose one memory completely and retain another in crystal clarity, as they would if memory was located in one area. The body hologram stores information from all the senses, and so when we smell something, it can trigger a memory just as powerfully as sight or hearing. Even this is another level of the illusion, because if the brain is a hologram, it must also be illusory. It is, like everything in this reality, the physical expression of a frequency field or resonance. Incidentally, the holographic nature of the body means the whole brain and body is involved in decoding the five senses, and not just the visual cortex and other areas of the brain associated with these specific duties. So you can obliterate a salamander's brain in any number of ways, and it will still have a normal life as long as you put a tiny piece of brain back in its head. You can teach a rat to run a maze, then remove any part of its brain, and it will still remember the run. You can remove 90% of a rat's visual cortex, and it will still perform complex visual tasks. You can sever 98% of a cat's optic nerves, and it will still see normally. These, along with many other experiments, strongly suggest that the brain processes images and stores information holographically, all parts in the whole, and the whole in all parts, because the brain, like a hologram, no matter how small the piece, can still reconstruct the whole. Michael Talbot wrote, "Our brains mathematically construct objective reality by interpreting frequencies that are ultimately projections from another dimension, a deeper order of existence that is beyond both space and time. The brain is a hologram enfolded in a holographic universe. What is out there is a vast ocean of waves and frequencies, and reality looks concrete to us only because our brains are able to take this holographic blur and convert it into the sticks and stones and other familiar objects that make up our world." In Michael Talbot's The Holographic Universe, he suggests our experience of the smoothness of fine china or the feel of beach sand beneath our feet is like an elaborate version of the so-called phantom limb syndrome, when amputees can still feel their missing limbs long after having been removed. In other words, there are two realities, like Bohm's implicate and explicate orders. In the implicate order, a china cup is just an energetic interference pattern vibrating at a certain frequency. But in the explicate order, after being filtered through the lens of our brains, eyes, and nervous systems, those interference patterns manifest to us as the look and feel of fine china. When asked, "So which is real and which is an illusion?" Dr. Pribram replied that both are real to me, or if you want to say, neither of them are real. Lynn McTaggart wrote, "Although the metaphor of the hologram was important to Pribram, the real significance of his discovery was not holography per se, which conjures up a mental image of the three-dimensional ghostly projection, or a universe which is only our projection of it. It was the unique ability of quantum waves to store vast quantities of information in a totality and in 3 dimensions, and for our brains to be able to read this information, and from this to create the world. Here was finally a mechanical device that seemed to replicate the way that the brain actually worked, how images were formed, how they were stored, and how they could be recalled or associated with something else. Most important, it gave a clue to the biggest mystery of all for Pribram, how you could have localized tasks in the brain, but process or store them throughout the larger whole. In a sense, holography is just convenient shorthand for wave interference, the language of the field." Itzhak Bentov said, "So here we are, all part of this great hologram called creation, which is everybody else's self. It's all a cosmic play, and there is nothing but you." In the 18th century, a Frenchman named Jean Fourier discovered a mathematical method of converting patterns into simple waveforms called the Fourier transform, a process which later led to the discoveries of both television and holography. When a video camera captures scenes on film, it converts pictures into electromagnetic frequencies, which are then converted back again by your television set. Scientists are now finding that this Fourier transform process is how the brain works as an electromagnetic frequency decoder. We have long known that through our 120 billion miles of DNA and RNA, our entire bodies are involved in a frequency decoding process. We know our ears are audio frequency decoders. Nobel Prize winner George von Békessy has proven that our skin responds to frequencies, and thanks to neurophysiologists Russell and Karen de Valois, we now know that brain cells in the visual cortex react and activate based on frequency patterns. Lynn McTaggart wrote, "University of California at Berkeley neurophysiologists Russell and Karen de Valois converted simple plaid and checkerboard patterns into Fourier waves and discovered that the brain cells of cats and monkeys responded not to the patterns themselves, but to the interference patterns of their component waves. Countless studies, elaborated on by the de Valois team in their book Spatial Vision, show that numerous cells in the visual system are tuned into certain frequencies. Other studies have showed that the human cerebral cortex may be tuned to specific frequencies. Pribram conjectured that these wave collisions must create the pictorial images in our brain. When we perceive something, it's not due to the activity of neurons themselves, but to certain patches of dendrites distributed around the brain, which, like a radio station, are set to resonate only at certain frequencies. It is like having a vast number of piano strings all over your head, only some of which would vibrate as a particular note is played. Dr. Pribram has conjectured that wave interference patterns are likely not created or received by any particular brain cells, but in the spaces between them. Dendrites, the tiny nerve endings of neurons, where synapses are fired, communicate with other neurons by sending and receiving electrical and chemical wave impulses. It is plausible that this is where wave frequencies are received and transformed into holographic images, because there are constantly millions of wave interference patterns crisscrossing here anyway. Lynn McTaggart wrote, "The fact that movement could somehow be represented formally in terms of Fourier equations made Pribram realize that the brain's conversations with the body might also be occurring in the form of waves and patterns rather than as images. The brain somehow had the capacity to analyze movement, break it down into wave frequencies, and transmit this wave pattern shorthand to the rest of the body. This information, transmitted non-locally to many parts at once, would explain how we can fairly easily manage complicated global tasks involving multiple body parts, such as riding a bicycle or roller skating. It also accounts for how we can easily imitate some task." Pribram also came across evidence that our other senses, smell, taste, and hearing, operate by analyzing frequencies. In Pribram's own studies with cats, in which he recorded frequencies from the motor cortex of cats while their right forepaw was being moved up and down, he discovered that, like the visual cortex, individual cells in the cat's motor cortex responded to only a limited number of frequencies of movement, just as individual strings on a piano respond to a limited range of frequencies. The color red in our explicit experience is really just an implicate wave interference pattern vibrating at a frequency of 400 terahertz. The color violet in our experience is really just a wave interference pattern vibrating at a frequency of 790 terahertz. Above the spectrum visible to humans are ultraviolet rays, X-rays, and gamma rays. Below the spectrum visible to us are infrared, microwaves, and radio waves. Our brains decode this small sliver of electromagnetic frequencies and create the perceptions and sensations we experience in our consciousness. Using